TigerBeetle live on Twitch, and it's a pleasure to welcome Dominik Tornow, Principal Engineer of Temporal.
Hey, hello. Thank you very much for having me. Super excited to be here.
Likewise, Dominik, awesome to have you. So Dominik, this all started with a sticker and a question about Temporal. Can you tell us a bit more about Temporal and what you do?
Yeah, so I'm a principal engineer at Temporal, and Temporal is a platform for durable executions. And durable execution is to a distributed system like a database transaction is to a database. So a durable execution is an execution that guarantees exactly one's semantics. So like a database transaction, a durable execution guarantees correctness by guaranteeing completeness. So if you want to learn more about Temporal, check out temporal.io. And if you want to learn more about durable executions, I'm going to post a link to my Strange Loop 2022 talk about workflows, a new core abstraction for distributed systems.
Awesome. So just to double check if I understand correctly, so workflows are like database transactions, but you can do atomic stuff with everything in the world. You just bring it together and move it around with Temporal.
It is analogous to a database transaction, but it is actually a function execution. It's a function execution that cannot fail and cannot time out.
Yeah. Wow. No, pretty awesome.
Yeah, I want to say it's like almost sci-fi stuff.
Yeah, for sure. Yeah, so I've been following what you're doing for some time, and I was so excited. Like, it was a pretty interesting story how we got connected. Back to that sticker, and Matt's watching, by the way, I think.
And back to the sticker. Actually, before we dive into technology, I totally want to give a shout out. So I see you're wearing the same T-shirt.
Yeah.
So the TigerBeetle artwork. And the TigerBeetle artwork is very unique and very, very likable. So I have the Beetle Gang here. The Beetle Gang, and of course, my absolute favorite, View stamp replication made famous. This is the sticker that started it all.
Yeah, and again, once again, we just owe everything to James Cowling. You know, if he hadn't done view stamp replication revisited with Barbara Liskov of MIT, there'd be no view stamp replication protocol. There'd be, no revisited protocol. There'd be no view stamp replication made famous campaign, no sticker. And it's kind of that consensus protocol. Dominik, you're into distributed systems. I'm also aspire to that. And so there was this sticker, and you just said, man, I need to get hold of one of those. And you were chatting to Matt, who literally sits next to me in the office. Or Matt wanted to ask you a question, and he saw I was following you on Twitter, and he came around to me and said, well, how do you know Dominik? I said, I don't, but he follows view stamp replication. So that's the protocol. This is a small world, like they say.
So you all bribed me with a sticker, and it totally worked.
Yeah, well, and thanks so much for coming on. It's awesome to have you on Twitch. Really, really cool. And yeah, just for everybody watching, Dominik is somebody who can just take something complicated and break it down systematically with crisp language. Really an incredible communicator. So I'm looking forward to. Yeah, it's a real pleasure that you actually wanted to come and chat about TigerBeetle, interview me for a change. So, yeah, really looking forward to it. By the way,
I am.
Over to you.
Mm-hmm.
Over to you. Yeah.
I am super excited when I discovered TigerBeetle first, and then I looked at TigerBeetle's code base. You already touched on a few of its cornerstones, right? One, for example, is view stamp replication, which is a consensus protocol, which are also famously complicated. And but when I came across TigerBeetle and I first looked at the code base, it is by all intent a complex system, yet it is very approachable. So it is, for me, it is pure joy to look at the TigerBeetle code base and dig into the individual concepts that we will all visit today, like the view stamp replication, like the deterministic simulation testing. So very approachable. It's one of my favorite examples that I recommend people to look at when they want to see either databases, consensus protocols, state machine replication, distributed deterministic testing. So it's really fantastic.
Oh,
Actually, now that we're on the topic, we can just jump right in, right? So we have mentioned.
Yeah, should I be nervous? Is it true that you've come here to destroy the principal engineer destroys the database? Maybe I've got good news and bad news. So I guess the good news is probably there won't be the destruction of a database. That's the good news. But the bad news is probably that's already happened. Like we had a warm-up talk and already you've spotted something really interesting. So we'll get to that later. That's the suspense part. But yeah, shall we get started? I'm ready.
Absolutely. So yeah, we mentioned TigerBeetle a few times already, of course, and pretty sure everybody knows TigerBeetle is a database, but TigerBeetle is not just a database, right? TigerBeetle is a special purpose database in contrast to a general purpose database. So maybe you could talk a little bit about TigerBeetle's mission statement and also touch a little bit on TigerBeetle's history.
Sure. Yeah. So I'll start with the history, then go to the mission. And history was pretty interesting for me because I'd never worked in payments before. And the next thing I know, I was doing analysis, safety performance analysis of an open source payment switch. And, everybody says, well, you can never build a new database because, Postgres is 30 years of everybody working on this thing. It's like this is tried and tested. All these databases are so old, and they're rock solid and amazing. And so that's true. But when you look at like these payment switches, which is a way to track money between banks or different systems, when you look at that, there is this mission critical database, yes, but around that is like 10,000 lines of JavaScript code to make a ledger. And there you've got concurrency problems and distributed systems problems and all kinds of problems and safety problems, performance problems. It's just problems. And then you look at that and you see, well, this actually looks like a database, the whole thing. And then you start to think, well, why don't we make a database like this? Because everybody in payments, at least from our team's experience, other people on the team had seen a lot of this just being everybody reinvents. It's like that old Lisp quote, yeah, if we're not familiar with
the
Lisp.
Greenspan's 10th rule. Was it the 10th? I believe it was the 10th rule. Yes.
Yeah. What is that quote, Dominik? You'll get it better than me.
Let me see if I can recite it from memory. Every sufficiently complex C or Fortran problem will have a slow, bug-ridden, informally specified of half of common Lisp inside of it.
Yeah. And we didn't rehearse this at all. This is just off the cuff.
We did not rehearse that.
Yeah, high five. That's amazing. I'm so glad I asked you to paraphrase. Mine was like 4 words, Yeah, and so we saw this looked like a database, and that was kind of the history. Like, let's build a database. It'll actually be safer because then we can do proper abstractions and things. And then I guess mission statement is a bit broader. So since then we realized TigerBeetle actually is just a good way to count things. It's a new category of database that's good at counting. So we have databases that are good at like time series or transactions or there's Redis with awesome data structures, but there doesn't actually seem to be a database open source that is just good at counting things. So that's our mission. Let's track business events or real world events. Let's track that. Let's count it at scale. So it's not even necessarily financial. It could be in-app transactions for games or energy as they switch energy back and forth into the grid. Could be like Twitter likes, let's count those, or let's help Elon count those. So many things can be counted. API usage, gateways for APIs like throttling. You could do leaky bucket. I'm still trying to figure all the use cases out.
That is That is very cool. You know, when you said it's like nobody's thinking they can build a database. It is really true. It is usually quite a daunting undertaking. I think there is somewhat there is movement, there is energy in the space when we look at like you mentioned Postgres and MySQL as the very mature solutions that have been worked on for a very long time. Then there are solutions like Vitess, which compose multiple MySQL clusters in one coherent cluster, right? So basically, then making use or reuse of that maturity, but trying to bring in horizontal scale. Other databases like CockroachDB or TiDB on top of TiKV from PingCap, they are all looking into the horizontal scalability of databases, but all of them are general purpose databases, right? They even advertise their compatibility with the MySQL protocol, with the Postgres protocol. So I am specifically also fascinated by the fact that you have a special purpose database, and as you said, it's good at counting things. Now I am not sure. Okay, I'll open that rabbit hole, and it's like, just ask you real quick, Joran, what is a database?
Okay, so here I'm just going to quote Alex Gajego, who was on our Twitch a while ago. I asked him the question. People like to say, it's only a database if it's SQL or things like that. And he quoted Amazon engineers who said, well, the database is the log and everything else is just cache. So I'll double down on that. Yeah.
I saw that Twitch stream, so that's also why I asked.
Yeah.
But when we look at TigerBeetle, so TigerBeetle is a cluster, but instead of looking into the cluster just yet, let's look at TigerBeetle itself as a black box. And can you talk a little bit about its data model? Actually, let me also for this post the link to the state machine, TigerBeetle state machine on GitHub onto the Twitch chat for anybody who wants to follow along. It's a direct link to the list of operations in TigerBeetle. Again, it's very approachable. So maybe you can talk a little bit about the data model, the accounts and transfers and operations around them.
Okay, yeah. So I guess the question is, if we want to count things, how do we do it? So we're just going to obviously have the thing that we're counting, right, and a little integer, and every time we want to count, we'll just bump that integer. And that isn't actually how TigerBeetle does counting. And I guess we all know the answer, but it's a few hundred years old answer. And the way TigerBeetle counts is the way that the Arabian merchants and the Italian merchants and then the whole world learned to count, which is double entry counting or double entry counting. And that's where you're kind of getting into like physics. So there's a bit of Newton's third law, I think, for every action there's an equal but opposite action, or law of thermodynamics, energy cannot be created nor destroyed, merely is transformed from one form of energy to another. And double entry is kind of like that. So you have Alice, you have Bob. Let's represent some kind of movement in the real world between them, and let's count that. So Alice, we're gonna decrease. Bob, we're gonna increase. So you have like a bit of a velocity. You have a vector showing you how it's moving and how much, which is different to just bumping a counter. Now you're actually saying, well, this is between two entities. Here's the direction. Here's the magnitude. And so yeah, for every debit to an account, which is maybe where for every debit to an account, there has to be an equal but opposite credit to a different account. And the whole reason why you pick this model for the domain is because it's like a financial error correcting code. If you take all the entities or all the accounts in the system, and if you look at each account is just like an append-only log. So every time you increasing or decreasing that account, you're adding an entry to the one side or to the other side. It's like a T for TigerBeetle. And so you've got the account, you may be debiting, putting a lot of stuff there, which for that type of account means it's increasing. Some accounts increase on the debit side, some on the credit side. But basically you've got running tallies on either, you've got two append-only logs for one account of all these vectors, and then you take the whole system, you add it all the accounts up, and it should equal 0. And then you know that nobody was doing any cooking in the books. So that's it's just it's a tried and tested way of counting things. But what's also nice is it's so simple as a schema. It's the simplest possible way to represent a lot of interesting information. And because it's so simple, this is what I learned from James Cowling, it's so simple, it then becomes highly composable. So you can take one of these T accounts and then like blow it up. And now like Iron Man, you've got these new atoms that you've discovered. And there's just like millions of T accounts, and you can represent any kind of state transition in the real world, like business state transitions. Or if your business grows or changes over time, you can just add new accounts. You're not doing like schema migrations on existing tables in the SQL sense. So it's a much nicer way to grow, as the domain grows. Did I miss the other part of the question?
Do not think so. Let me actually also post one more link into the chat, because I saw that TigerBeetle released an FAQ this morning, and there is also more to read about the double entry accounting, with a quote from Goethe, fellow German.
Yes.
So his genius is unmatched. Yeah. And
that quote,
okay,
by the
so
way, there's a little story there. So I was in Italy, in Padova, in April this year, and somehow I ended up at I think the world's oldest botanical garden, because all the world's oldest and coolest things are in Italy or in Germany. It's either Germany or Italy. So next thing, I was in this botanical garden, and then there was this like special house, there was some special like gigantic plant inside that's a few stories high. So I go inside the house, it's this big palm tree, and it's actually called Goethe's palm, and I think it's 500 years old. So the palm was so old that it looked like Yoda. It was all furry, and it was just incredible thinking of Goethe's quote, double entry counting is the finest invention of the human mind. Everybody should introduce it into the economy of their household or their business. And then seeing Goethe's palm, that inspired him, for some of his agricultural works or botanical. Yeah. So.
Okay, that is very cool. That's a very, very cool backstory. So one thing that you mentioned, and I think it's also mentioned in the FAQ, is that double entry accounting is basically a business level error correcting code. So then can we say that it is an invariant for TigerBeetle, that whatever operation TigerBeetle processes and therefore moves from the previous state to the next state, that the invariant, that everything within TigerBeetle sums up to 0 at all times, is also enforced by TigerBeetle itself?
Yes. Dominik, can you correct me on that? Is there a case where we aren't, or where we might not have been if we weren't careful?
Okay. So we can go into that very quickly. Let's just summarize real quick. So on TigerBeetle, we have two objects or two entities. We have the accounts, and we have transfers on accounts, and it is basically, as you said, it is write only or append only. So transfers are only created.
Yes, and a transfer is kind of that vector. So the information in one transfer it's a unique ID, 128-bit for idempotency. You've got a timestamp, which gives you date and time of the real-world transaction. You've got a little numeric code, which tells you why this transaction was done. You know, this was taking, this was going out to buy a coffee, or this was buying a laptop for work. You know, different types of codes to capture different types of expenses, or maybe it's not an expense, maybe you bought a car and it's an asset. So you've got a little numeric code, and it's basically just a pointer to, and then the organization can decide what those codes mean. Then you've got obviously an amount, and you've got the account that you're going to debit, the account that you're going to credit, and that's a transfer. So ID, timestamp, a description, which is a numeric description, an amount, and the direction.
Fantastic. And you also mentioned idempotency. So that is something that basically every application developer, every system developer in the distributed world needs to wrap their head around, but also general purpose databases do not come with that out of the box. So TigerBeetle has IDs to deduplicate out of the box. So that is part of the core data model.
Yeah, and
very cool. That makes
that's one of the hardest problems for massive systems that, you know, do billions and billions of, because they've got billions of transactions. How do you do idempotency across so much, you know? So TigerBeetle gives that to you at that kind of scale. I was chatting with someone who did the ledger at a massive car rental or car ride-hailing service. And I don't know who you can guess which one of them it was, but they were saying, you know, idempotency is really hard at scale. So
you know, now I'm exaggerating a little bit, but if you solve my idempotency problem, you already solved 90% of my problems. And then I put Temporal in the mix, and that solves the rest of my 10%. So it's like, we're solid. We're solid on that one.
Yeah.
Okay, so then you were already mentioning if there is a potential invariant violation. So far we looked at one specific TigerBeetle cluster as one black box, but of course one TigerBeetle cluster does not exist in isolation, right? So it's like you have multiple TigerBeetle instances that actually form coherent systems, or that need to be composed into coherent systems. So now we are not talking intra TigerBeetle cluster, we are talking inter TigerBeetle cluster, and I believe TigerBeetle also implements a variant of the two-phase commit protocol to make inter cluster transfers possible.
Yes. So how this started, we didn't think we would need it. We kind of looked what people were doing and tried to abstract, like, you know, how Ruby on Rails came out of Basecamp. We looked at a real open source payment switch, traced all the SQL queries, wrote up all the business logic, and worked out this is really what's going on. And the big idea is you've got a scheme or a switch. It's basically it's the person that's keeping score, and you can have a few friends, and you're going to designate someone that whatever they say, that's the score. That's the system of record. That's the switch. And then as friends, you can start saying to the switch, okay, Alice wants to send Bob 100 units. And that goes through the switch, and the switch coordinates that. It's a coordinator, and it's a little bit like two-phase commit. So Alice will want to send the money, so she will make a note on her database that it can be any database that she's using in her tech stack. She's going to send 100 units to Bob, so she puts that aside. She tells the switch, okay, I want to send to Bob 100 units, the switch says, okay, Alice and Bob, I've got your books because I'm the authority here. So Alice, I'm going to reserve or some of those 100 units that you can't spend it to somebody else. I'm going to reserve those 100 units. I'm going to reserve it also that it's going into Bob. Maybe there's business logic that we can't give Bob too much money. Otherwise there's a, export control problem or whatever. Then the switch will notify Bob, hey Bob, today's the day, Alice sending you 100 units. Bob says, okay, cool, I got this. Bob also records on Bob's little database, whatever Bob uses, maybe it's in memory only. So he might lose that, which actually would be very, very bad. So let's not use that example. So, okay, Bob's using a proper database. He's going to make a promise that, sure, he's going to accept this money, otherwise it would get lost. So everybody has now promised. That goes back. Bob says to the switch, good, I'm good. The switch then commits. And the commit is basically, okay, we knew it was pending from Alice to Bob. Now it's final. Bob, you've got the money. Alice, you don't. And then all the way back to Alice. So that's kind of what's going on. And there's a lot of complexity how to do that in code. So what we realized is that it's not enough just to track money within a system, like with double entry. It's not a pure ledger. What a lot of people are doing is they're using a ledger in the context of distributed systems to talk to other people, friends who want to have a system of record. And so actually, like TigerBeetle gives you these primitives in the accounts struct. Accounts now have debits pending, debits posted balance, credits pending, credits posted balance, and that way you can actually, track in-flight movements of money and get it all right. Yeah.
I saw there is one of the operations is for TigerBeetle is called create transfer. However, there is actually there are two sub operations to that. One is, if I'm not mistaken, the single phase transfer, where the transfer commits immediately, and another one is a two-phase transfer, where a transfer is pending and needs another message to be actually committed. And as you already said, we had a preparation for this interview, and we were talking about the two-phase commit protocol. And I would say the two-phase commit protocol is arguably the most famous protocol, or maybe the gateway drug into distributed systems.
Yeah.
I think every computer science student will learn about the two-phase commit protocol as one of their first distributed protocols. But the two-phase commit protocol is also not the most resilient / reliable. So as a quick reminder for the audience, so in the two-phase commit protocol, you have a transaction manager or transaction coordinator, and you have multiple resource managers. The transaction coordinator needs to, as its name implies, coordinate. So it sends a prepare message to the resource managers for them to prepare to commit, and the resource managers will then reply with, okay, I can commit, or they will say, no, I cannot. And at that point in time, the coordinator will then take the votes. Only if all resource manager voted for yes, we can commit, does it then instruct the resource managers to commit. If one says I cannot, it instructs everybody to abort. Now, if one of the resource managers crashes, that is okay, that can be handled, since then that absence of a vote can be interpreted as an abort. However, if the transaction coordinator crashes, that is an iffy scenario, because the resource managers, after they promise that they are able to commit, they need to stick to that promise. They cannot revert. And Joran, maybe you can elaborate a little bit what we discovered in our prep call.
Yeah, so thanks, Dominik. That's an awesome explanation. So one can think of the transaction coordinator as the switch because it coordinates. You can think of the resource managers as Alice and Bob. And if the switch goes down, then there's no fun and games because nobody can. If the switch comes back up, it's fine. Things can carry on. If the switch ever forgets, it's all over because the system of record has lost data. So where are things at? That's the switch, the coordinator. The resource manager, they can crash, they can come back up, but they can never forget what they promised because otherwise they've promised 100 to Bob. They forget that promise. Now they promise that same 100 to Charlie, to Belinda, and then money is just being invented and printed. So they can't forget what they promised. And at the same time, if the transaction coordinator kind of messes up, then those promises at the resource managers are stuck. That money is forever locked up. Now, the money was supposed to move, it was promised, and then the coordination failed and it never moved. Or what can happen is maybe one of the resource managers wants to promise, the other one doesn't want to. Now you need to have a timeout in the coordinator to go, okay, we're going to abort and go back, and that's all fine. So TigerBeetle has that primitive where as you do the pending transfer, because remember we were always seeing the switch, we were focused so much on the switch for the where TigerBeetle is running. The switch has the timeout in TigerBeetle which rolls it back, and that's all fine. And then Dominik and I discovered, just chatting, Dominik discovered this, well, what if Alice and Bob are also using TigerBeetle? Now everybody's using TigerBeetle. Now they're also using pending transfers, right, to talk to the switch. Well, you can't really do, you can do that, that's right. But there you've got to be really careful, and this is something it's a new use case we haven't really focused on, and we need to document this. This is what you discovered, Dominik, is that the timeouts can only be in the switch or the coordinator. They can't be for Alice and Bob, because Alice and Bob make promises, and those promises can never roll back. A lot of databases like Cockroach operate on the principle that you can have a lease, for some period of time, and so long as everything else is under that period of time, you're safe. If you go outside of that, all bets are off. So you could kind of do that, but it's not correct, and it's not the TigerBeetle way. So we got a great little bit of database destruction or docs destruction where we can definitely go and it's just a thing where you switch the use case around and oh wow, be careful there. The timeouts there shouldn't happen for the resource manager. So thank you, Dominik.
Yeah, the great part about TigerBeetle's data model and also the append only is that in this case, as you said, once a transfer is promised, for example, once 100 units are promised, you cannot go back on that promise until you hear back from the transaction manager. However, other databases, they take, for example, a row level lock, right? And then God forbid, a table level lock. And then this is locked, right? In TigerBeetle, yes, the 100 units are locked up at that moment. However, that doesn't prevent you, if you have enough funding, from continuing making transfers. Yeah. So the impact is in most cases the impact is limited. So that is pretty cool. And what I really enjoy about this, before I go there, let me post a few more comments in the chat. This is a YouTube link to Martin Kleppmann's distributed system class about the two-phase commit protocol, one of my favorite explanations and introductions. So that is a very cool one. I also want to share a blog post from Murat Demirbas, the two-phase commit protocol and beyond, that shows clearly with the TLA plus temporal logic of action, TLA plus model what you described, when the transaction coordinator goes down and forgets what it already decided, how can you recover from that situation? Actually, you cannot. We are running in the FLP impossibility. That is an impossibility result that doesn't make a lot of appearances in everyday life, but in this situation it does. So that's very cool.
Yeah, and that's what I wanted to add on that point. That's kind of why TigerBeetle isn't just a database, but it's a distributed database, because that switch can never go down. It's got to be highly available, because otherwise there's no fun in games. It's also got to be highly durable, because it can never forget. So that's what we were seeing. You know, all these ledgers are being built with Postgres, like standalone node. And obviously in the cloud you get replication. It can be very expensive, but you really need high availability, durability, and that's why TigerBeetle, like, we focus so much on storage faults, because you can just never forget, because disks do forget. I've seen it, you know, like firsthand. I've seen MySQL get corrupt, and I never used it again. Like, and then there was all the storage fault research showing that so many of the databases we love are actually, you know, there's latent correctness bugs because of how they truncate the write-ahead log, you know, the commit log at startup. If they see a little bit of bit rot in the log, they think, oh, that was because of power loss, and they truncate the whole commit log, and there, you know, the switch has just forgotten the whole year of transactions, or if the log is very long. But that's why we just focused on storage faults, because you can just never lose data. And what's interesting is you can't just run the database on ZFS either, because the 2018 research from Wisconsin-Madison was showing that if you want to do consensus protocols properly, you can't just have a network fault model, you have to have a storage fault model. And the whole, you know, the replication has to be integrated with the local storage of each replica. Otherwise, you have these storage faults and they propagate through the whole cluster. They spread. And that can affect Raft or Paxos. You know, Raft and Paxos are famous for being formally proven, but they were only formally proven with a network fault model, never a storage fault model. So I just can't wait for the day when we start seeing this more, because you can really have these systems can forget, you know, and so that's why TigerBeetle is kind of like, this thing is so highly available, so highly durable, that it's fine now. The two-phase commit problem, we're okay, because we expect it's never going to fail, like, you know, or at least it'll never lose data.
This is very cool. So in the lecture by Martin Klettmann, he also talks about how can we make the two-phase commit protocol more reliable. And there are basically two solutions. One is the resource managers themselves can coordinate via totally ordered broadcast. And in a distributed environment, in a cloud environment, there's just no chance. So you may be able to implement that optimization of the protocol if you operate in the same data center. But the other one is what you just said. We need to make the transaction coordinator highly available. And that is when I think about TigerBeetle as the underpinning for the transaction coordinator for the switch, that's almost a no-brainer. That's just fantastic. Yeah. So it's a very cool way of thinking about TigerBeetle as the ledger, as a piece of paper where the transaction coordinator remembers its decision. So that's very cool. Yeah. One more thing I would love to add to the two-phase commit protocol. The two-phase commit protocol, if the transaction coordinator crashes and the resource managers are tied up. So Bob's 100 units, $100, 100 euros is indeed tied up, is a fantastic example where failure handling actually needs to go beyond the software system, needs to go outside of the software system and into the system. And that means somebody probably needs to take manual action. It is either an administrator that needs to or operator takes administrative operative action and resolve this manually and tell the TigerBeetle that acts as the resource manager either void this transaction or actually do settle this transaction. And that reminds me, this failure handling is something that we do not often talk about, right? Where we need to elevate the failure from the software system, into the real world. But there is a great paper by Pat Helland, Building on Quicksand, that touches on a lot of different aspects of modern systems. And one is memories, guesses, and apologies. And he argues that in that moment when you actually you leave the software system and you enter the system, your failure handling is basically driven by apologies. You need to apologize to the customer or the user that their money was tied up for an uncanny amount of time, but you just rectified the situation.
And sometimes the customer says it's too late to apologize.
That is also true. I don't think that Pat Helland had a recipe for that one.
Yeah, there's always got to be music in there somewhere, you know. And I always also, Dominik, what you've been writing about this quite a lot. The idea of where's the best place to handle failure. Like, is it the platform layer, if I understand correctly, or the application layer? You know, where and it's been interesting because with TigerBeetle's replication, we have a message bus abstraction. Each replica, each machine in the distributed database, and again, it's just a single binary. So you've got like 6 machines, run a TigerBeetle binary on all of them. And again, just a disclaimer, we're not production ready yet. So if you're running it, this is just, you know, experimental lab stuff, looking to the future, designing for TigerBeetle. But again, so you've got 6 machines, they're running this binary, they talk to each other over the network, and you've got this network fault model, so messages can get dropped or delayed or replayed or reordered. But actually, like so many of our systems, we build on TCP, and we think, well, we're good, we're ordered, delivery, reliable, whatever. But TCP actually, it's like a leaky abstraction because, and there was a great paper about this the other day, how we need to rethink like networking in the data center because TCP is just got, and it was such an awesome paper. I can't remember what it was called, but it was getting to this idea of messages. We need to think again of, let's send a message. So I'm going to send a message as replica 1 to replica 2, and that message can get lost but it kind of shows you what we realized in TigerBeetle is we had this message bus abstraction. Under the hood, it's doing TCP connections to talk to replicas, but the abstraction interface it provides maps one-to-one with the network fault model. So when you want to send a message to another replica, it's like fire and forget. It's like send this message to this replica, and that's it. And you don't know, it might get lost. It'll probably get sent over TCP. It might not because TCP connections fail. You have to do another one, then all bets are off. But it kind of worked really well for TigerBeetle because aligning the abstraction with the underlying fault model and moving the error handling into the application was the right thing for a consensus protocol because a consensus protocol has that network fault model. But I've been just thinking about your writing on this and as a way of thinking back on what we did and yeah, sometimes you handle it lower down if you can, but having a nice message bus abstraction like this in TigerBeetle really worked out well. Yeah.
Actually, that remind me, how much time do we have left?
We're still good, another 12 minutes, yeah.
Okay, wonderful, because we do need to dive into that cluster. So up to this point, we mostly treated the TigerBeetle cluster as one black box, but it's, I think, time to open that black box for the last 12 minutes and look into it. As you already said, the TigerBeetle itself is one binary, can be spun up multiple times, and it composes into that coherent cluster. And I would say the glue, as you already mentioned, the glue of that cluster is a few-stamped replication, so that keeps the cluster in sync. I do want to post also the link to the paper of the few-stamped replication. and the protocol-aware recovery for consensus-based distributed storage into the chat. Maybe you can say a few words, but I will also post the fused and replication made famous talk that you had on Zig Showtime. So anybody who's interested can catch up. There, Joran talks about the fused and replication in more detail, but maybe you can spend a few minutes talking about it.
Thanks, Dominik. So yeah, protocol-aware recovery is such a brilliant paper, and it's kind of, not everybody is paying attention to it right now, but I think in 10 years it's going to be monumental. Like that paper was a line in the sand, and it said it's now a new era for distributed databases. The way they're designed has to be changed completely. It's a very tough paper to read. You read it the first time, it looks okay. You read it the second time, and it's very concerning. What it implies for all our distributed systems. The way they do the log is it's all isolated, so it's local storage, global consensus, just two abstractions. They're not integrated, and that is, the paper shows, is neither correct. You can have cluster data loss, and you don't get this high availability. So that paper is basically the architecture of TigerBeetle, how the global consensus replication, viewstamp replication, is integrated with our storage engine for storage faults. And storage faults are very much part of the consensus protocol in a way that for Paxos and Raft they never were. So whenever I love Diego Angaro's Raft thesis, and I keep coming back to it, and I read it again and again, and it's fantastic. And every time I press Command F on my Mac and I search for corrupt, storage fault, latent sector error, misdirected write, and it's not there. And it has to, protocol-aware recovery, the paper is saying, look, it has to be there, because otherwise it's not correct, it's not highly available. Obviously, in industry, people are doing this. There's lots of people that are, not always in open source. So the protocol-aware stuff has been in some proprietary, some of the big FANG, but it's not yet in open source. But yeah, and then viewstamp replication is just awesome protocol. So yeah, Dominik, you've posted the link, so I think that's, I can just say that viewstamp replication has got a more state-of-the-art leader election algorithm than Raft. Raft was 2 years after viewstamp replication revisited, and it missed it. So it came later, but 2 years earlier there was a better leader election algorithm, in my opinion, because it's more, it was based on Barbara Liskov and work in practical Byzantine fault tolerance, and it's the algorithm has got more information in it. So if the leader fails, the rest of the cluster have a very, very good idea of who the next leader is. So they can detect, firstly, they can detect the failure of the old leader quicker than Raft. And once they've detected it, they can isolate the old leader and move to the next much, much quicker. And there's much better guarantees on that. Everything, there's better guarantees, which we always like in TigerBeetle. So yeah, and it's just a nice protocol. The paper is just as accessible as Raft. But it's pretty interesting. Raft starts, I think, with leader election and then goes into normal protocol. Viewstamp replication starts the other way, and that's what I love about the paper. And it can start the other way around, just normal replication, and then what do we do if the leader fails? It can do that because it's just got in my opinion, just a more advanced algorithm. And it's a simpler algorithm. There's no randomness, no dueling leader problem.
So I want to say as a summary to all of that, it's like, if in 10 years protocol-aware recovery for consensus protocols is mainstream, then I want to say that is TigerBeetle's and yours doing. So it's like, let's keep our fingers crossed. It makes the jump into mainstream. And since you already mentioned some of that, I want to post the last link here to the chat, and that is, we're jumping right into the TigerBeetle simulator. for two reasons. Because number one, for a few more minutes, I would like to hear your thoughts on deterministic simulation testing. But also, when you look at this link, you will see the network options, storage options, state machine options. So you can actually see the failures that TigerBeetle can take into account. And as Joran said, you see that there are storage faults in there. Line 129, clear as day. One of the reasons I really enjoy looking at the TigerBeetle code. But yeah, if you could spend a few minutes talking about the deterministic simulation testing, that would be fantastic.
Thanks. I'll never forget, Dominik. We had a one-on-one after Matt introduced us, and I just said, "Hey, Dominik, can I show you like our simulator?" And you're like, "Yeah, sure," and then showed you, and you loved it. So I mean, and you kind of
was blown away.
Yeah, they were so nice, you know, and that experience made me realize, wow, we should talk more about this. But this is kind of now touching on why should we build a database? How can you have the courage to go and do it? And there's a few things, like we've seen, it's a new era for databases. The way we design them has changed, protocol recovery, storage faults. There's new safer languages as well, like why write in C, C++? You've got Zig, you've got Go, you've got Rust, new safer languages. So you've got IOU ring, whole new way of doing IO, like the whole hardware's all changed. But this is the big thing that gives us like strength, is deterministic simulation testing. This is like Jepsen, but now imagine like Jepsen, where you can run Jepsen. Jepsen has a limit on how long it can run because it's extremely expensive. It's a black box test, so it has to collect all the events. Afterwards, go and figure out if everything was correct for strict serializability, you know, which is brilliant at. It's got amazing optimizations, but it limits how long you can test. Also, you have to run the system in real time. So if you want to find a bug with Jepsen that would take 20 years to manifest, of 20 years of runtime operation, you have to run it for 20 years. And if you find the bug, you can't find it again because the test isn't deterministic. The software, it's thread scheduling, it's different disks, latency, everything changes. So deterministic simulation testing, like pioneered by Foundation DB, with that, it's different. You can tick time in a while true loop. So you can speed up time. You can do 20 years in like one day. And you can test very, very far. You don't have that CPU complexity of checking strict serializability. You can check it instantly as state transitions happen. And you can do storage fault injection and all this interesting stuff. And on top of it, if you ever find a bug, you get a little number, a seed, and you just drop it in Slack to your team. Everybody with a little single binary, add the seed as a command line argument. They can reproduce this whole world of different latencies that were all simulated. The latencies are simulated of the disk, of the network, the partitions, the faults, storage faults, all of that, the whole movie. You can replay the whole movie just from that seed. And then you can debug it and fix it. So you basically, it's amazing because, before these systems would take 10, 20 years to build. Now you can build them in like a year or 2 years and then get the same amount of testing in like a month or 2 months of just pure CPU runtime. You can really get a lot of testing. It's a force like Fred Brooks is always talking about no silver bullet, but DST is a silver bullet because it literally will make your team so much faster. And again, like, you have to build a new database design if you want to do this kind of testing. You can't just take off the stuff off the shelf, Rocks or LevelDB. It's not deterministic. It doesn't have a storage fault model. Yeah.
So figuratively speaking, it defies the laws of physics because it violates the laws of Heisenberg. Yeah? Who clearly said you cannot look at it. And with deterministic simulation testing, you can actually look at the Heisenberg.
Yeah.
So it's very cool.
The goosebumps it gives you when you see this running and you see that every replica is like radioactively corrupted and it just works. Like it's, I just love it. It's magical feeling, and all credit to, the researchers that did Protocol Aware and Foundation DB. Yeah.
It is also deterministic simulation testing for me, similar to formal modeling, model checking. It is a thinking tool. It makes you think about your system, understand your system better. And I want to encourage everybody really check out this link that links to the TigerBeetle simulator, because you will not only see the configuration for the deterministic simulation testing, but also what Joran mentioned, how you need to build your system differently, and you can clear as day here see the individual subsystems that TigerBeetle built, the storage abstraction, the network abstraction, that make all of this possible, the foundation of TigerBeetle DB implementation.
Well, yeah, thanks so much, Dominik. We're coming into land, but maybe, I don't know, shall we give like a sneak preview of what's up in Feb 23?
That is all up to you.
Yeah, so I mean, this has just been a blast we're basically talking distributed systems, right? So, and a little while ago I said I knew Dominik loved kitesurfing and I'm getting into it, and a few other people I know. So I said to Dominik, hey, why don't we do, people don't often talk about systems, but we like to. We aspire to do systems. Maybe we don't know how to get into systems programming or distributed systems. Nobody understands Paxos. Why don't we do something where, let's do this crazy conference and we'll teach systems 2 days, and then everybody hang out. So yeah, just to let everybody know, if you're watching in, build the anticipation. I don't know, Dominik, over to you. What's up in Feb 23?
Okay, February 23, we have the systems conference coming up. We're gonna talk about distributed systems, software systems, but also generally system thinking, system modeling, and how to approach complex dynamic systems. Get solid mental models that lets you reason about complex systems and helps you design and document your entire applications. Yeah. And Joran and the TigerBeetle folks came up with the idea and also with the organization, and I am super excited and super happy.
Yeah. Yeah, it's going to be awesome. Temporal's going to be there. We're going to be doing hands-on workflows, amazing stuff. Andrew Kelly, Laurice Crowe of Zig Foundation, they're going to be there. Jamie Brandon, Derek Elizen of NATS, Alana Mazouv of ReadySet, awesome caching, database caching. If you haven't seen ReadySet, go take a look. A few more awesome speakers lined up. Yeah, and then some of us are going to go do some kite surfing on the weekend, because this is all going to be in Cape Town. So Cape Town, Feb 23, 9th and 10th. Details are coming. Follow our Twitter. And yeah, just wanted to say so much to
cool.
Yeah, so much thanks to you, Dominik. I've just loved chatting like this.
Thank you very much. Me too. That was definitely the highlight of my day. That was a fantastic conversation. Thank you so much for your time.
I really appreciate it. Thanks to everybody for joining us. See you again soon.